Yeah.
What's up, calculus students? Uh, let's get into derivatives. What the heck is a derivative? What are we going to be spending the rest of the year talking about? Definitely the rest of the semester. And yes, rest of the year. What is this thing called a derivative? Well, we start with talking about how slopes equal how quickly a function is changing. Slopes equal change. And we start with slopes that we have found before, which is just like slopes between 2 points on a function. For example, if I say here's x cubed between the point at x equals 2 and x equals 3. If I say what is the slope, you'd be able to find it. But would you know what it meant? That's like the new thing, is making sure you understand what the slope of 2 points that connect on a function mean. And that's why we're here. So to find the slope, you need a slope formula, y2 minus y1 over x2 minus x1. So this would be slopes connecting 2 points. You use this formula. So I need the 2 points. I need to plug in 3, get 27, plug in 2, get 8, and then I just calculate the slope. y2 minus y1, x2 minus x1, and you get 19. But what does that mean? We say that on average, this function x cubed is increasing. We're going to say either increasing or decreasing. We can kind of look at it if we look from left to right, or we can look at the sign of this value being positive. We say the function is increasing at approximately 19, on average 19 y's per x. This is an important statement. So I'm going to say on average, f of x is increasing by 19 y's per x over the interval. Okay, so we say that the slope that connects 2 points on a function gives the average rate of change. So the slope of 2 connecting points on a function, or we call this the slope of a secant. A secant line we talked about from geometry is a line that crosses through a circle twice. We're going to call a secant line a line that connects 2 points. Okay, so slope equal change, slope over an interval, average rate of change. Let's go ahead and just find some slopes. The rest is just practice plugging in and finding slopes. And then writing the statement. And you can even write slope secant. Turns into 9/3, which is 3. Now, this tells us on average how quickly the function is changing. And if we understand how quickly a function is changing, we know a lot about the function. And this is why calculus is such an important subject. It's like we are just analyzing how quickly something is changing. And by understanding that, we know a lot. So focusing on how quickly things are changing is what this class is about. Okay, I'd say on average, f of x is increasing 3 y's per x over the interval 0 to 3. Okay, Some more slopes just for practice. Let's think 0. Okay, 2 pi over 3 is in the second quadrant. Cosine SOHCAHTOA, the adjacent, negative a half. So tall 30, 60, 90 triangle. Y2 minus Y1, X2 minus X1. I get negative 3 halves over pi over 3. Keep change flip. Negative 3 halves times 3 over pi gives us negative 9 over 2 pi. Now, when we have answers that are fractions, usually students like to say these are the y's and these are the x's. But I'm not going to do that because I know I can take a fraction and put it over a 1 and say this is y's per 1x. And that's always what we want to do so that we're able to compare our values, have it be a unit rate of change, a y's per 1x. So when you answer fractions, know that the fractions can go over 1. Now we see that the slope is negative. What we'd be able to see is that this function is decreasing on average. It's going down on average over the interval 0 to pi over 3. So f of x is decreasing. That slope being negative, think about negative slopes. F of x is decreasing on average. I should probably say on average, f of x is decreasing. Negative 9 over 2 pi y's per x over the interval 0 to pi over 3. I'm not going to write that down. Let's try this one. F of 4 is 2 to the negative 4th. That's 1 over 2 to the 4th, which is 2, 4, 8, 16, 1/16. Thanks, Mr. Messner, for giving us fractions. F of 1 is 2 to the negative 1, which is a half. So I need to do 1/16 minus a half over 4 minus 1. This is 8/16. Multiply the top and bottom by 8. So I have negative 7/16 over 3. Great. I have negative 7/16 times 1/3. Great. 16 times 3. I got 30 and I got 18/48. So I have negative 7/48. So I would say, since I see that negative number, on average, my function is decreasing. That many y's per x. Okay, and this is like introduction. This is like stuff we kind of know how to do, just maybe we're making sure we interpret it correctly. We're decreasing 7/48 of a y per 1x on the interval from 1 to 4. Okay, so boom, slopes of secants, on average, how things are changing. If I give you a graph, could you do the same thing? Sure. Well, I just need to find the slope that connects the 2 points. Here's a point at x equals 2. This is an x interval. If students have difficulty understanding this problem, they don't realize like the interval that we're talking about is an x interval. So x of 2 and x of 4. I have my y of 2 and my y of, I don't know, let's just call this negative 2 and not have to worry about fractions. So I will do negative 2 minus 2 over 4 minus 2. I get negative 4 over 2, which is negative 2. And there you can see that negative value. We can see this negative slope. It's important to understand the signs of slopes. Going up from left to right, positive slope. Going down from left to right, negative slope. Okay. And the value, the slope of this line is negative 2. The interpretation is that on average, this function decreases 2 y's per x. If I went down 2 over 1, down 2 over 1, I could travel from one point to the other point over the interval. Okay?
Really? Look at these kids, math rock star.
Okay, let's do another one from -1 to 4. That's an x interval. Here's x is -1. Here's the point, -2. And here is x is 4. Here's the point. We're going to call that -2. I don't want to deal with fractions. So we can see, this is a good example. This line is horizontal. Now we should know that horizontal lines, the slope is 0. We could calculate it if we wanted to. -2 minus -2 over 4 minus -1. And I can see like I don't increase or decrease with my y's. My y's have no change over an exchange of 5, which means my slope is 0. 0 y's per x. Now we can see the function doesn't stay constant, but we can say on average we go down as much as we go up. So on average, we're kind of back to where we started. We don't increase at all over this interval. Now, what do we say? It doesn't increase, doesn't decrease. We say it's constant. Or we could say increases 0 y's per x, decreases to 0 y's per x. We won't be picky about that. And then we got -2 to 1, 2, 3. Oh, it's the same thing. So we're good. I'm not going to do it. It's another 0, so it's constant. Might as well change this to 2, just so we have like different values. Yeah, that's good. Let's change that to 2, just so we can have a positive value. Okay, there's that line connecting 2 points. We call this the secant line. The slope of this line tells me on average how much the function is changing. So I'll do 2 minus 0 over 2 minus -2. The y is 2, the y is 0, the x is 2, the x is -2. And I get 2/4 or a half. Turn that into y's per x. So we'd say on average, my function is increasing. We could see that positive slope. A half of a y per x on the interval -2 to 2. Okay, this is review. Like this is not that important. It's important to introduce what is important, the concept and the use of a derivative, okay? Because we change to like not a average rate of change. On average, we want to know, and this is what calculus is all about. Calculus is all about how quickly is this function changing at a moment. So like how quickly is this function changing at 1? Well, the concept, if we continue to think about slopes equaling rate of change, the line that could just touch this, that kind of shows the slope right here at this point. This slope would give me how quickly the function is changing at that point. We call this the slope of a tangent line. Tangent lines from circles just touch a circle. If the slope over 2 points gives us the average rate of change over that interval, the slope at a point will tell us how quickly the function is changing at that point. That's calculus. Slope at a point, or the slope of a tangent. And the question we then, got into is how do we calculate the slope at a tangent? And we looked at this function x cubed. We looked at a different point, but it's like, I ask you, how quickly is the function changing at x equals 3? And you might be like, okay, well, let's try to use the slope formula at 3. And you like plug in 3 and you get 27. And you're like, well, that's just 1 point. don't I need 2 points to calculate the slope? And you're like, maybe I used the point twice. But then you realize, no, I can't use the point twice because I get 0 over 0. But that's an indication that like we have a limit. We're going to approach a certain number so that there like is a slope there. It's just using this 0.327 doesn't help. And again, this is very much like not the most important. What we're about to do next, introducing the equations, the slope equations, the M equations, that's what's really important. But this is kind of like conceptually how we think about what we're doing here. So instead, what we decided to do is, hey, here's my function x cubed. Let's, instead of focusing on 327, let's use 2 points around 327 because I need 2 different points to calculate the slope. So we can do 2 and 4. We can do 2.5 and 3.5. We can 2.9 and 3.1. And then we can think about getting really, really close to the left and to the right and using 2.99 and 3.01. Now I'm going to actually show a quick and easy way to do this using your calculator. You guys don't actually have to do this. This is not something that you have to do on your quiz because it's just more of a conceptual understanding of how we marry a limit to a slope formula, which was Newton's beautiful discovery. He was the matchmaker that brought the limit to the slope formula. Boom, they had a baby. We called it a derivative. Okay. Here's the easiest way to do this. I'll show you. I can graph y equals x cubed. And then I can actually here create like a quick slope formula where I will use F4. I'll be able to like plug in values into this to get a y2 minus a y1. Hey, you owe me a quiz.
Yes. Monday?
Yeah, free period.
Yes, I have a first lock on them.
Can you do it then?
Yes. Yeah, because it only takes 15 minutes.
Okay, so I'll put it in the testing room.
Yes, sir. How's that? Remember that?
Yeah.
Okay, great. Thank you.
All right, thanks, bud. Here's my y1, and then here's my x2 minus my x1. And I get 28. Okay, so my slope from 2 to 4 is 28. On average, my function is increasing 28 y's per x over the interval 2 to 4. And then I'm going to just change it so that I have my different values. If you know how to use a calculator, you know how to insert. I don't actually like how we're doing this at 3. I wish we did it a different value. But whatever. If you're actually doing this homework, you're probably wondering, like, what's going on here? I don't like how the slope is going to actually equal the y value. If I were to change this, I would. Okay, that means on average, the function is increasing 27.25 y's per x over the interval 2.5 to 3.5. A small interval, which means like this value is kind of telling me what's going on here. But let's do better. Could I do 3.1 and 2.9? Again, not a big deal for you guys to be able to do, but it's more marrying the concept of a limit to the slope formula. And this was Newton's beautiful discovery of the marriage. We are marrying a limit and a slope, and all of a sudden I got slope is 27.01. So over this interval, which is a small interval, on average, I'm increasing 27.01 y's per x. But like, since my interval is so small, you know, there's not that much that the function can do over the interval. So like the smaller and smaller the interval, the more you're really just focusing on one point until we get to 3.01 and 2.99.
Thank you.
And we get this value 27.001. Now, is this a realistic process that we could do without a calculator, or we could do at other values? Well, it's like without a calculator, no. With a calculator, with some sort of machine or computer, we could program in something to just like, hey, look a little bit to the left, look a little bit to the right, and use 2 points very close and give me a slope. And actually, that's what your calculator does when you ask it to find a derivative. Like, go ahead, if you have a calculator, find math 8. And you don't know this notation yet, but this means take the derivative or find the tangent slope. And you could plug in the function, you could plug in the point. And it's not magic what your calculator does. Your calculator just has programmed into it, hey, let's use a point a little bit to the right of 3 and a little bit to the left of 3 and plug that in. And actually, like, there you go. They actually use 3.001 and 2.999, like just like 1/1000th to the right and 1/1000th to the left. And like that's all they do. So it's like something that computers can easily do quickly is find the slope at a point by looking at slopes of 2 points very, very close together. Okay. So yes, if we had a computer, easy. Yes, with a calculator, easy. Without a calculator, not easy. So here comes Newton. And Newton's like, yo, we need a different way. We understand the concept of the marriage of a limit and a slope formula. He's like, cool, we got to get these two together. We got to be able to use it. And what he decided and what he discovered is that we could use this not really using numbers, but using x's. And we could get an equation for slopes. So like a slope or an M equation. And he decided to call it an F prime equation. Now, this is where it's very important, guys. This is when you're like focused, okay? He noticed that if you have a function F, that it has a unique slope equation. So like this F prime, you're not going to call it F to the first. It's just a little tick mark. This is F prime. This is going to be giving you slopes of your original function F. So like here, F, you got X's and Y's. Here, F prime is going to have X's and not Y's. I mean, they are Y's, but X's and slopes of F. And right now, visually, we don't know exactly what the slopes of F are, but we can at least approximate. So I know that like this would be a slope of 0. This would be like a small positive slope. This would be like bigger positive slopes if you're thinking about slope values. Here would be negative slopes. Here would be more negative slopes if you're thinking about slopes being y values, okay? And what we can do is visualize this slope equation. And how we do that is like we just take some points, maybe some points in between, and we think about what are the slopes at these points? We can go over here, we can go over there. You'd be like, okay, well, it starts out with a slope that is very, very negative. And you got to be able to do this. Then we have a slope that is a little bit less negative here. Then we have a slope here that is 0, it's horizontal. We have a slope that is positive. Not sure how positive it is. It's probably not steeper than this slope. We have another slope that's 0. We have a slope that is negative. And then we have another slope that is more negative, okay? So I'm going to try to like plot these values, not their exact values because I don't know the exact values, but just like an approximation of the values over here. So I'm going to say, okay, I started here, maybe like here was -1, here's 0, here's 1. but I started a little bit to the left of like this x equals -1, and a little bit to the left I had this most negative slope. So I'm going to plot a slope. This negative slope I plot right here. My cursor comes back, I'll do the other ones. I see my slope at -1 is a little bit like less negative. It's closer to 0. It's less negative than this negative. So like here at -1, I'm going to plot, a less negative slope. Now here between -1 and 0, I have this slope of 0. So here's me plotting a slope of 0 right there. And then here at 0, I have this slope that's positive. It's about as positive in terms of its steepness compared to this slope. It's like less positive than that. So I'm not going to go all the way up here to like super positives. I'm going to kind of go to this like less positive slope location. Then in between 0 and we'll call this 1, if this was -1, if this is 1, this is -1. So for the x values, we're kind of try to keep things aligned. So here between, I have this slope of 0. Then here at 1, I have a slope that's like a little bit negative, and then I have a slope that's more negative. And I create, this visualization of the slopes of f. We call this f prime. And if you continue to plot more and more slopes, you'd be able to continue to see that the slope values would fall nicely and create this beautiful graph of what's like a parabola. Now, you don't have to be perfect for this homework. Like if you have it look like a V, all good, you're fine, don't worry about it. But then Newton realized, there is an equation for this. There is some equation, some expression where it's like, if you told me what this was, I would be able to plug in x's and get m's. This is Newton's beautiful discovery, that you don't have to use slope of points, but rather you can marry the limit and the slope formula, and boom, that would help you develop equations of slopes. And this is what the rest of like this semester is about. The equations of these slopes, which will tell you very quickly how quickly the original function is changing. And we are going to spend the rest of this semester using this to understand this more. Okay? And for today, I'm going to be like giving you the equations. I'm going to tell you what they are. You don't have to worry about finding them. We're going to start finding them next class. Okay? So let's pick some points. I can see I'm not really going to 1. I'm before 1. Here I have a point here that's an important point that I'm going to plot. Here at 1, I see that slope. Okay, so I have like 5 points, 7 points, and we can see that don't really get to 1, and we start to the left of -1. I have a very positive slope. I have a less positive slope. I have an even less positive slope. I have a slope of 0. I have a not very negative slope. I have a more negative slope, and I have a most negative slope. So I kind of need like 3 levels of like slopes. Again, these are going to be x's. These are going to be slopes of f. And I'll say like super negatives, less negatives, 0, positives, more positives, most positives. And I have a most positive as my first point, a less positive here. At -1, I am a little bit positive. That's important. Don't put a 0 here at -1. At -1, I am a little bit positive. In between, I have a 0. And then at 0, I have a little negative. And then I have a more negative. And then I have a more negative. I don't even get there. So like over here. And we create like this kind of graph. It should look like a line, honestly, but if it doesn't, no big deal. It's just like, yo, you can see it's unique. This equation's slopes look different than that equation's slopes. Yeah, of course. They're two different equations, they're two different functions. So the slopes and how the function is changing is different. This one is a cubed graph. Its slopes look like an x squared graph. This x squared graph, its slopes look like an x graph. Oh, that's interesting. Maybe keep that in mind. Here's some x to the fourth graph. Let's kind of jump in here. So I can kind of see -2, -1, 0, 1, 2. I will pick some points. One, 2, 3, 4, 5, 6, 7, 8, 9. See if you can do it quicker this time. Super negative just to the right of -2. Super negative just to the right of -2. Less negative in between. So less negative in between. I got a 0 here. At -1, I have a 0. That slope is 0. I have a very tiny positive in between -1 and 0. Tiny positive. I have a 0 slope at 0. I have a very tiny negative in between 0 and 1. I have another 0 slope at 1. I have a positive, and then I have a more positive in between, and then at. And all of a sudden, it's like, wow, that's really cool. The slopes of f that started with this x to the fourth function turns into an x cubed function. And Newton's like, yo, this graph exists. Let's find the equation of the graph. Let's use the slope formula in a different way, not using numbers, but using letters. A couple more. Let's just kind of go quickly through these. Positive, 0, -0, positive. I'm just going to do 5 points. So to the left of -1 and between -1 and 2, I have a very positive slope.
It's kind of fuzzy. Figure out a little bit. It's like for me, like right now. Awesome, man. I can just jump
All
on
right, so super positive slope, 0 slope, negative slope, 0 slope in between, positive slope. Interesting how that works out. It's probably this 0 slope's a little bit left of -1. We don't see this symmetry. Well, we want to see a little bit of symmetry. So we get something like that. Okay, so again, an x cubed graph creates a slope graph that looks like an x squared. There's an equation for that. A couple more, and then we'll get to the beautiful thing for the rest of the year. This is a negative slope, 0 slope, positive slope. If you don't get this, like make sure you just go step by step with points, understanding slopes, and don't copy this down. Practice. And this is an interesting one. The slopes are all positive, but they're all consistent. So these slopes are all positive, but consistent. So all of a sudden, this y equals mx plus b line turns into just a y equals m line. Now, Newton said, yo, let's marry the limit and the slope formula in such a way that we don't really worry about using numbers, rather we use functions at x's. And he developed this equation, and many of you know this as like a difference quotient. Yes, if you marry the difference quotient, which gives you like the slope between any 2 points h distance away, but you make the h distance 0, you get an equation for the slope of a tangent. Yeah, if h is approaching 0, the 2 points are getting infinitely close together. So if you have 2 points infinitely close together, boom, you're really talking about the slope at this point. It's like what we're doing with limits. It's like, yo, if you're plugging in 2.99999, you're going to essentially get the same thing as if you plug in 3. Well, if you take 2 points, one at 3.00001 and 1.2.99999, and find the slope, you're essentially finding the slope at 3. Okay, so this is the slope of the tangent at just any x value. Here you can see it's like, well, I'm going to plug in c. I'm going to get the slope of f close to c, at c. Now, do we even? Okay, then we talk about. Actually, we talked about it earlier, so let's make sure we get this. Yo, this. Come back here. Everybody come back here. Hope you're here. Come back here. Come back here. Come back here. This is so important. The instantaneous rate of change of a function, we call it IROC, instantaneous rate of change, can be found by looking at the slope of the tangent. We are going to focus on this so much this year that we're going to give it a special word, and that word is called the derivative. These three things are the same. They are synonymous. One means the other. If I ask you to find the derivative, you are not only finding the slope of the tangent, but you're finding the instantaneous rate of change. If I ask you, hey, find the instantaneous rate of change, you're finding the slope of the tangent. You're finding the derivative. If I ask you, find the slope of the tangent, blah, blah, blah. Okay. So they're all the same. And we're going to do it the same way every time. We are not going to use our calculator. Okay. Unless we have like our calculator handy. Instead, we are going to find the slope equation and we will be able to plug in x's to get m's. That's it. It's easy. It's a lot easier than like slopes and limits. It's like the limit formula helps us develop the equation and it's easy to use the equation. Okay. So, cool. We'll get there. We're almost there. The last page is the most important. This is just making sure you understand those formulas. You'll see questions like this. So here's a function f of x. They're asking you like, what are the values, positive, negative, or 0 for all of these limits? And it's like, ugh. Well, it's like, let's look at this one. There's no limit. It's just slope, y2 minus y1 over x2 minus x1. This is actually meaning the slope between the points C and D. Oh, those values are negative. Now, I'm going to stop using negative and I'm going to say it's less than 0. Less than 0 is the same as being negative. Let's be a little bit more proper in our mathematics and not say equals negatives. We'll say it's less than 0. All right, why don't we go to do this one? This is just slope between 2 points at C and A. Okay, we cool with that? I think we should be cool with that. We can see that slope is positive. It's greater than 0. Now, the other 4 have a limit and a slope formula tied together. Now, this is where it's important. This is slope, but it's the slope at D. This would be the slope over the interval C to D. This would be the slope as well at D. What is the difference between these two? It's like they're just the same form of one another. Like if you plugged in 0, you get f of D minus f of D over 0. If you plugged in D, you get f of D minus f of D over D minus D, which is 0. So like these are the same things, they just look different. So if I asked you, what is the slope at D? You would say the slope at D, this slope right there is a negative slope. What if I asked you this? Well, you can say, okay, it's just a slope formula, but like the distance is approaching 0. It's the slope at, it's marrying a limit and a slope formula. So it's a slope of a tangent. This is the slope at x equals c. The slope at x equals c is this slope right there. That slope is 0. What about this? Well, it is a marriage of a limit and a slope formula. This is going to be the slope of the tangent. It's going to be the slope or the derivative at x equals b. At x equals b, you can see this slope is negative. Positive. Now, I could go beyond this and ask you to order these from least to greatest. That's kind of what the next question is asking, like order these from least to greatest. And now I'm changing it up. Instead of I'm giving you limit notation, I'm going to give you this notation f prime of a, f prime of b, f prime of 0. All you need to know, and this is what Newton did, is like, hey, every f has a slope graph. We will call the slope graph f prime graphs. Y value of an f prime graph is a slope value. This value right here tells me this slope right there. Got it? So like the slope of f is an f prime value. That's just what we're deciding. So if I look at f prime of a, this means the slope of f at a. We're going to make sure you guys know this is the graph of f of x. What is the slope of f at a? The slope of f at a is a negative slope. So f prime of a is negative. Cool. What is the slope of f at b? The slope of f at b is very minimally positive. I'm just going to say it's positive. Small positive. What is the slope of f at 0? The slope of f prime, translated to the slope of f at 0 is more positive. The slope of f at 0 is more positive. It's bigger positive. What is the slope of f at c? F prime, translate the slope of f. The slope of f at c, the derivative of f at c, the instantaneous rate of change at c looks like it's 0. What is the slope of f at d? The slope of f at d is a little negative. This is a big negative. All right, so if I'm going to order these from least to greatest, I would say the slope of f at a is the biggest negative number, and then that's less than the slope of f of d, which is a small negative, closer to 0. Then I have the slope of f at c, then I have the slope of f at b, and then I have the slope of f at 0. Okay. Now we get to like where the rest of the year starts. Turns out, using this formula, the marriage of the slope formula between any 2 points of f, h distance away at any x, you get an equation. Guys, it's easy to find these equations, but for right now, I'm just going to give them to you, okay? And you can see how like Newton actually used this to develop what's called derivative rules. We're not going to worry about using this like I showed you in class. Newton took care of it. Instead, I'm going to say, hey, you got x cubed minus 1, f prime is 3x squared. Now here's, everybody's like, this is where we're locked in because this is so important. If this was the graph of x cubed minus 1, which is not, but let's say it is. If this was the graph of x cubed minus 1. This equation would be the graph of 3x squared. This is very like what we did in class. I'm telling you that is. You don't have to find it, but you got to know how to use it. Now, what's great about this is if you plugged in a value, I plug in 1 into f prime. I'm finding the slope of f at 1. I plug in 1, I get 3. That's an m. The slope graph has an equation. Plug in x's, you get m's. 3 is the slope right here. That value is now known, no longer approximated. This slope is 3. How do I know that slope is 3? Because I found the equation of the slopes of f. I can plug in x's and I'll get m's of f. I am telling you what the f prime equations are for this first lesson. You just got to know how to use them in the most basic forms. I ask you, what is f prime of 3? We already kind of like looked into it. Like we were using our calculator, we were going at 2.999 and 3.001. We said it looks like it's going to be close to 7. Well, if I plug 3 into this, I get, close to 27. If I plug 3 into this, I get 27. Cool. What does this mean? The slope of f at 3 is 27. You read f prime as the slope of f at x equals 3 is 27. But now you can make that translation to the slope of a tangent is the rate of change of the function. You could say at x equals 3, f of x, which is x cubed minus 1, is increasing 27 y's per x. We don't have to say over the interval. We already said at x equals 3, this is how quickly the function is changing. And if you know how quickly the function is changing, you know a lot about the original function. And this is going to be applied in many, many different areas and different places. But we're going to try to keep it as simple as possible from the start. Cool. Now, could we write an equation of the tangent line and then could we see it? And it's beautiful to see it. Well, we talked about in class how like equations for lines are easy. All you need is a point and a slope. Well, here, if we plug in x's into f, we get y's. If we plug x's into f prime, we get m's. We get m's of f. So just remember, like this. Plug in x, get a y. But don't forget this, which I said up above. Don't forget about it. It's still there. But here's the key. When you plug in x's, you get a slope of a tangent to x cubed minus 1. So all you need to do is plug in 3, get 26. Plug in 3 to get the slope of the tangent to f at 3, and that's 27. Here is my y1. Here is my x1. Here is my m. Okay? Now, it's not always 3x squared. I know that was the example we used in class. You know, it's not always that. Every f prime is unique to f. That's why we call it f prime. I use Newton's marriage, slope formula limit. I plug this into it, or I use what he developed, which is a derivative rule. And I get that if you have the equation x squared minus 5x minus 2, that the slope equation for that is 2x minus 5. So, like, again, this is like different for a lot of you guys. You are not used to having an f and then using something else to tell you about the original equation. Usually if I ask you, hey, let's look at x squared minus 5x, what is it? X squared minus 2x. x squared minus 5x minus 2. If I say, hey, tell me information about x squared minus 5x minus 2, you're used to just using x squared minus 5x minus 2. But this is where calculus is beautiful. This is why Newton's a genius. Newton's like, yo, you want to know about x squared minus 5x minus 2? You need to actually look at this equation. And this equation, 2x minus 5, is going to tell you all you need to know about x squared minus 5x minus 2. Because you can plug in x's into that equation, and you will get the slopes of that equation. This is just like beautiful, and I hope you understood it during the lesson. So, what is the slope of the tangent to f at x equals 4 and x equals 2? Well, I have the slope equation, where if I plug in x's, I get m's. Now, again, I plugged it into 2x minus 5. So I have 2 times 4 minus 5. 2 times 4 minus 5 is 3. So this is translated as the slope of f at 4 is 3. Which then gets translated to the instantaneous rate of change of f at x equals 4 is 3. Or f is increasing by 3 y's per x at x equals 4. Or you can say the derivative of f at x equals 4 is 3. They're all the same. What about at 2? 2 times 2 minus 5 is negative 1. What does this mean? I'm going to go right to the third statement, the most important statement. F is decreasing by 1 y per x at x equals 2. And now I want an equation of a tangent line. So now I need to finish off with a y minus a y1 equals an m times an x minus an x1. I'm going to show my handiwork in a second. Because like it's one thing to kind of just do it. It's another thing to see it. So at negative 1, so I'm choosing a different spot. So now I need a point and a slope. Well, remember, you plug in x's, you get y's. You plug in x's, you get m's. All right, so I just need an x. Okay, negative 1's my x. I need a y, plug it in here. I get 1 plus 5 minus 2, which is 4. My computer's really slowing down right now. And if I plugged in negative 1, I'll get an m. I get negative 2 minus 5, which is negative 7. That's an m. That's a y. That's an x. Y minus 4 equals negative 7, x plus 1, x minus negative. It's easy. Yo, it's easy. If you are given an f prime equation, it's so easy to find slopes of f. So easy. Thanks, Newton. Okay. What's the instantaneous rate of change of f at x equals 1? Oh, I don't know. Oh, wait. An instantaneous rate of change is the same as the slope of the tangent, is the same as a derivative. We have the equation of the slopes of the tangents, where if I plug in x values, I get m values, 8 minus 6. What does this mean? The derivative of f at 1 is 2. The slope of the tangent of f at 1 is 2. Or f is increasing by 2 y's per x at x equals 1. What about at negative 1? Negative 8 minus negative 6 is negative 2. F is decreasing 2 y's per x at x equals negative 1. Or you could say the slope of the tangent to f at -1 is -2. Or you could say the derivative of f at -1 is -2. They're all synonymous. They're all the same. What's the equation of the tangent? Well, I already have the m's. This is an m. This is an m of a tangent. This is an m of a tangent. Now I just need the y's. So I'm going to go and plug in -1 into the original equation. I get 2 minus 3, which is -1. And then I'll plug in 1 into the original equation. I get 2. Okay, that's a little annoying, but whatever. At x equals 1 of y plus 1, that's y minus -1, equals m of 2, x plus 1. At x equals, that was -1. At x equals positive 1 of y minus -1 equals the same m, but opposite, x minus 1. Cool. Again, if you have an equation for f prime, which I'm finding for you, you just need to know how to use it. It's easy to find how quickly functions are changing. I found that for 8 square root x, that the f prime equation is 4 over square root x. Now, starting next class, you're going to have to find the f prime equations. Right now, you just got to know how to use it. And again, this is the most important page of this entire homework. I'm asking, what is the slope of the tangent to f at x equals 4? Now, let me just show you really quickly. What if I say, hey, computer program, give me the slope of 8 root x at x equals 4. All the computer program does is plug it into a y2 minus y1 over x2 minus x1 slope thing using 4.001 and 3.999. And it says, oh, you get something close to 2. It's going to be 2. Cool. So this is my program using numbers. You can see probably need to be more exact. I need to go closer to 4. Let me just show you really quickly. If I did 8 root x, hope this isn't confusing you. You won't have to do this process. It's not a realistic process. Here, use the slope formula, but at 3.999 and 4.001, I'm literally telling my calculator to just use these 2 points very, very close to 4 in a slope formula. Newton's like, yo, this is not something that human beings can do quickly. This is something that computers can do quickly. But what can human beings do as another way? Well, we can understand the existence of the f prime graph. We can find the equation of the f prime graph using the marriage of the slope and the limits. Once we find the equation, boom, now we have the key. We have the ticket. We have the ticket to all of our slope problems. We have the equation where if you plug in an x, you get an m. Look at that. It's the same value that my calculator said, only this is exact, whereas my calculator is getting closer and closer and closer, approaching. It's kind of showing me the limit. What does this mean? F of x is increasing 2 y's per x at x equals 2. That is an m. That's an m of f. This is the slope of the tangent to f at 4. What is the equation of the tangent at 9? Okay, I need a y minus a y1 equals an m times an x minus x1. And then we're going to go into Desmos and show you the beautiful stuff, okay? So let's find the m. Plug in x into f prime, get an m. 4 over square root 9 is 4/3. That's an m. That goes there. Okay, plug in x's, get m's. What about f of 9? 8 root 9 is 8 times 3, which is 24. This is a y. This is the x. That's the x. This is the slope of f at 9, which is 4/3. So I get y minus 24 equals 4/3 x minus 9. And now let's look at all of our beautiful, beautiful, beautiful work if my computer doesn't break before then. Like, part of calculus that's great is being able to see your handiwork. Desmos is literally going to break this computer, but let's see. Y equals x cubed minus 1 is the equation. I found a tangent equation. Y minus 26 equals 27x minus 3. Ba-bam. There is the tangent line to the graph at this point, 327 or 326. Great. First one, check. Next one. We looked at x squared minus 5x minus 2. Cool. I found two equations. No, one equation. I found the equation of the tangent at x equals -1. So I have the equation y minus 4 equals -7x plus 1. I'm sorry I'm so messy, but honestly, that's why I have to do this video, so you can hear what I say. Well, bam! Look, we have the equation of the tangent to that graph. Now, what's important about this is like that slope of that line tells me how quickly this function is changing at that point. We are decreasing by this many y's per x. And the extension of how we can use this is like great. We know how quickly things are changing. How quickly things are changing. Powerful. X to the 2x to the fourth minus 3x squared. Cool. Kind of looked at like one of these x to the fourth ones earlier. Y plus 1 equals 2 times x plus 1. I made a mistake. I mean, this is a great way to check. How do I know I made a mistake? Oh, well, there you go. Mr. Messner screwed up. This is why we can check our work. This should be the -2. This should be the +2, right? If we have 1 plugged in, we get 2. If we have 1 plugged in, we have the point -1. We have the slope of +2. I got them all flip-flopped. My bad. So I need to change this to a -2. And then voila, there we go. Look at that. And then at the same time, we have the other equation. Y plus 1 is +2x minus 1. But bam, look at that. There are certain questions in calculus we'll have to answer. It's like, where do those two lines intersect? And like you can find that value and stuff like that. There's lots of fun questions that we will be answering in the future. It will just get like more tricky, more interesting, but we'll get there one step at a time. Right now, what you have to understand is slopes equal change. That's step one. Do you understand that slopes equal change? Check. Slope of a secant, average rate of change. Slope of a tangent, instantaneous rate of change. Good. You got that? That's step one. Step two. There are equations of the slopes of f that are unique to f. F's slopes can be graphed. F slopes can be graphed, and we can see the equation for f slopes. If we have the equation for f slopes, boom, we know a lot about f. We know all of the slopes of f at any point. It started by marrying the limit and the slope formula, but then it's used not numerically, which is what you guys like to do with slopes, is just like plug in numbers. Rather, it's used with x's. Many of you in pre-calculus did that. you like plugged in x's and you got some like expression for slopes h distance away after you simplified algebraically. We don't have to worry about that. We are just going to go straight to getting the equation of f prime. Just make sure you know how to use it. Okay? And here's our last one. Bam. It's beautiful. It's beautiful. Okay? If you don't understand, rewatch the video, come in and ask me questions. If you're using a tutors, I hope you're watching this video. And starting next class, it's going to be your job to find the f prime equations. Okay? But you're going to find out. That's not that bad. It's not that hard at all. Thanks, Newton. You're the best. All right. See you out there. Peace.